In this video, we're going to take the sound you created using the additive synthesis waveform generator and create a formula which we can graph. But to first do that, what we need to do is convert our frequency into a mathematical period. And to do that, we need to understand a property of a sound wave called its wavelength, which is equivalent to its mathematical period, which is about how long something takes to repeat its cycle. First, let's take an equation from physics, which says the frequency of a sound wave times its wavelength is equal to the speed of sound. And the speed of sound, at least the sound that we perceive with our ears, is constant. It is equal to 343 meters per second. And so we can use this fact now to actually take a frequency and convert it into a period, and then convert that to figure out what our coefficient b is in our equation. First, let me write in the symbols here. So F for frequency, and wavelength is represented by this upside down Y looking figure called lambda. Again, another Greek letter. We're going to go ahead and replace lambda with a mathematical term, which is the period, which we use the Greek letter tau for. And that's going to equal 343. So I can solve this equation pretty simply by dividing both sides by F, and I will get that the period is equal to 343 divided by whatever frequency. What you're going to do is you're going to take your fundamental frequency, that note that you picked out from the chart, and you're going to write it in this equation. So in my case, I had chosen 305 hertz, and so I'm going to divide 343 by 305, which is approximately 1.125. Please don't round too simply. Don't make these whole numbers or even one decimal place. 2 or 3 decimal places is recommended. Next, I'm going to remember that the equation for the period is 2 pi divided by b. And so what I can do now is write that this is equal to 2 pi divided by b. And I want to solve for b because that's what I need to write my equation. To make the math a little simpler, what we can do is invert both fractions. We can flip them both over. So I'm going to take this one and make it b over 2 pi, but then that means that this side of the equation needs to be 1 over 1.125. And then now all I need to do to solve for b is multiply both sides by 2 pi, which will cancel this out, and then I will use my calculator to go 2 pi times 1 divided by 1.125, or just 2 pi divided by 1.125, because multiplying by the 1 part isn't going to do anything. And here I get b is approximately 5.587. Okay, so now we found b in our equation, but it's actually going to be much, much simpler for us to find a. And let me show you. So say you'd created this sawtooth wave. Well, down below, right along here, is the amplitude of all our waveforms. And so we don't actually need to figure out what a is. It's something that is written out exactly what it is. We don't need to do any calculations. And so the a from this equation comes from our very fundamental, and if I can get out of the way, you can see hopefully that it's 1. So in this case, a is 1. Now once we have this, we're not actually going to calculate C and D at this point, because those will be what our effects do to our sound, what our delay or phaser or pitch vibrato, that's what they're going to imply and induce on our sound. And now what we're going to do is we're going to create a list of the amplitude and the frequency of all the tones that make up our complex tone. And both of these are actually fairly easy to find or calculate. When it comes to the frequency, as the frequency doubles, B also doubles. When the frequency triples, when I want to graph the frequency that is H2, all I'm going to do is double B from H1. And when I want to do H3, I'm going to triple it. When I want to do H4, I'm going to multiply it by 4. So as I go along here, I'm going to multiply B by whatever number harmonic it is. So again, I calculated all these frequencies by taking that top frequency and then multiplying by 2, and then taking the top and multiplying by 3, then taking the top, multiplying by 4. That's all you're doing to create those other harmonics. Whatever harmonic it is, you're multiplying by that number. Finding the amplitude is even easier because it's written right here. This is a row of numbers that shows you what the amplitude is. Just write those down. Once you have all those amplitudes written down and all the corresponding B, notice that I put A1, B1, A2, B2 to make sure that I could connect the two together. Then all you need to do is write your expression. So for this, all I need is amplitude is 1 times the sine and then this is B, 5.587 theta. Now I don't need to write the 1 here, but I'm going to go ahead and do this just for this exercise. Here I'm going to write 0.5 sine of 11.174 theta, and so on. And notice that I didn't write y equals. We'll get to that step later. We're just writing our expressions. All we need to do from here to write our equation now is to write y equals the first equation, and then we're just going to add up all the rest of the equations. And while it is a bit of legwork and time consuming to do, that's all you need to do to write the equation. Now I want to give a caveat here, because in the additive synthesis waveform generator website that we used, there were a couple of other options. One was to change that positive into a negative, which means to flip the wave over, and it would change the nature of the waveform, but not really what you hear. And another option was to change, if you clicked where it said sine, you could change it into cosine, and again it would shape the waveform, but not necessarily what you hear. If you decided to click one of those things to make your graph look more interesting or your waveform look more interesting, just make sure you change a plus to a minus if you did that, or a sine to a cosine if you did that.